Pivot your life with ECI.
On July 30th, 2016, Luke Aikens jumped out of an airplane at 25,000 feet without a parachute. When he landed about 2 minutes later, he was still alive and unharmed. We all intuitively know what can happen if you jump without a parachute. So how did Luke make it out alive? The answer lies in the concept of drag. When an object is dropped, it accelerates earthward at a rate of approximately 32.2 feet per second. In a perfect vacuum, this acceleration would continue indefinitely, but in Luke's case, he could count on the density of air, the area of his body, and its drag coefficient to finally stop accelerating and maintain a terminal velocity of 120 miles per hour. It was then just a simple matter of stopping, which was accomplished with a custom net. Can you think of a time when you experienced or saw drag in action? Perhaps when you've driven a car, ridden a bike, thrown a ball, or dropped a piece of paper, you've noticed that there is an invisible force acting against the direction of motion. This is drag force. In this tutorial, we will discuss what drag is, the equation, how to use the equation, some applications, and other details about drag. For information on how to use software to simulate drag, refer to Part 2 of this series, SOLIDWORKS Drag Simulation, or just click the link in the description. There are two types of drag, pressure drag and friction or skin drag. Pressure drag happens when a body moves through a fluid at a high speed, thereby causing a pressure differential between the front and rear of the object. This essentially creates a suction behind the body, causing it to slow down. Drag acts similarly to friction in that it slows the velocities of factors in the system. But on its most basic level, drag is simply impulse momentum in action on a microscopic scale. As the particles in the air collide with the uneven texture of the body, the mass and velocities of each create a negative force respecting the direction of travel. The sum of all these negative forces adds up to the cumulative drag. To further understand the concept of drag, let's look at the equation. The force of drag equals the drag coefficient times 1/2 times the density of the fluid times the velocity squared of the object with respect to the fluid times the surface area of the object. The drag force is directly proportional to each term on the other side of the equal sign, so to influence the drag force, one or more of the other variables must be changed. Since pressure equals force over area, then force equals pressure times area. If we use the equation for dynamic pressure in place of pressure, we get F equals 1/2 rho v squared A. To finish the equation, we must add the coefficient of drag, which accounts for the shape, compressibility, texture, and several other factors. We thus get the equation F sub d equals C sub d 1/2 rho v squared A. If you'd like to research this further, think about how drag force affects these applications. The shape and design of a race car, the curveball thrown by a pitcher, and competitors in the Tour de France. In this tutorial, we've learned about pressure drag and skin drag. We've covered the derivation of the drag equation and discussed some practical applications of drag. How well did you understand this video? See if you can write down or recall the equation from memory. To reduce the force of drag, should you increase or decrease the surface area? If you have any questions, comments, or ideas for improvement, please leave them in the comments below or contact us directly through our social media. And remember, click that subscribe button.